Hey everyone, this is the first video that we are going to be doing for pre-class videos. The first class that we have is going to be on mediation, moderation, and conditional indirect effects. Those of you who have taken ARM 2 with me are going to be very familiar with mediation and moderation, though less familiar with conditional indirect effects. Some of this will seem like a review, some of it will not. When we get to the very end of this, we'll kind of pull in these things, the mediation and moderation, into a single framework. This year, instead of using SPSS and process, which is what we did in ARM 2, we're going to shift focus to Mplus, and we're going to be using Mplus to calculate both mediation, moderation, and indirect effects. And I'll show you some tricks in class on the best way to do this. So let's start out a little bit by talking about clinical trial designs. We have a few different types of clinical trial designs. The first are treatment efficacy designs. And these are important when it comes to both mediation and moderation. For treatment efficacy, we typically have some sort of an experimental design or a quasi-experimental design in which we're have a control group, either that we've designated as a control and randomly assign people to receive treatment or control, or some series of treatments and control, or we have a quasi-experimental design where we have tried to identify potential control groups or differences that may pre-exist that we didn't actually assign. So, for example, I'm doing a study in Alabama where we're looking at the effects of an intervention on school bullying, and there were some schools that we were just simply not able to get to or include in the intervention because of restrictions that were placed on us by the school. And so those schools were often designated as control schools. In contrast, we did have some schools that we could assign to control, and so it's kind of a mix of experimental and quasi-experimental. The last one that we have is like a comparative treatment efficacy design. And so we did a study here recently that looked at two different treatments for alcohol-related consequences in college students. We didn't have a true control group. We had a control or a group that got what's called basics, which is a brief alcohol screening and interventions, and then a group that got an expectancy challenge curriculum. And so we were comparing the effects of two active treatments without a true control. Um, in contrast, we also have what are called dismantling studies. So for the first one, for these efficacy designs, we're often talking about moderation, right? We're talking about the effects as a function of some other variable. And so we might be looking at treatment as a moderator variable. For dismantling designs, in contrast, we're really trying to identify either the magnitude of effects that a treatment has on some sort of outcome, or a mechanism that the treatment affects that then has an effect on some sort of mechanism. And in both of these cases, we're talking about some sort of a mediated effect, right? The treatment affects M, which then affects Y, and so, or the extent to which treatment affects M and subsequently Y. Anyway, those are two kind of basic clinical trial designs and how they fall into mediation and moderation. Most clinical trials are a combination of these two things. All right, so let's talk a little bit about moderation as just a review. Moderation, of course, is when one variable affects the relationship between two other variables. Um, for example, when impulsivity affects the relationship between impulsivity and alcohol problems amongst men and women. So what are the variables here? Well, if alcohol problems is your outcome variable, and impulsivity is your predictor variable, your independent variable, then alcohol problems would be your dependent variable. And then biological sex would be your moderator variable in this case, right? you're looking at the association between impulsivity and alcohol problems and examining the extent to which biological sex changes that relationship. And so moderation is always when some variable changes the relationship between two other variables. In class in the past, I've called this the volume knob effect, right? Like one variable is able to turn up the volume or turn down the volume on the relationship between two other variables. Often the way that we examine a mediated effect, or I mean a moderated effect, is through the use of Aiken and West's plus and minus one standard deviation. That's going to sound very familiar for those of you who took ARM 2 with me. Another possibility is the Johnson and Neiman technique, where we calculate the regions of significance. In this case, we don't rely on some arbitrary plus or minus one standard deviation. We identify, at least in the data set that we have, the exact spot where an effect changes, either becomes zero or becomes statistically significant. And of course, the way that we calculate a moderated effect is just a multiplicative term, right? We multiply x times m. And so here is the basic kind of schematic of what we're talking about. You can see that this looks like a structural equation model or a path model. And that's what we're going to be working with throughout this class, are various types of path models. So for the test of moderation, you multiply the x variable by the m variable, and so you would have in this first instance the slope of x plus just I, or you know, your error, and then in the next one we would add in the main effect of the moderator right here and the interaction between x and m. And this really is the test of moderation. If this is statistically significant, then we will go back and substitute in high levels of m and low levels of m to examine this effect when this is at high and low levels. Oftentimes we'll say that this is the effect when everything is held constant at its mean. Now when we center variables, and we're going to talk about that in just a second, this and this from these two different equations should be exactly the same, right? Because in this equation, assuming that it's centered, then the mean effect of m is going to be 0. In x times m, the mean effect will be x, whatever it is, times 0. And so, yeah. All right. When we are describing moderation, we don't need to talk about the main effects, especially the main effects of m, but we do need to talk about the conditional effects. Now you can say the main effect of x is this when m is held constant at its mean. The other way that we say it is the simple effect of x is whatever when m is at one standard deviation above its mean, and the simple effect of x is this other value when m is at one standard deviation below its mean. And you know that I prefer to use the plus or minus one standard deviation, but I'm also a huge fan of figures, and the Johnson-Neiman figure just looks cooler. So here's a figure that's using plus and minus one standard deviation. This is from a paper that we published looking at alcohol pathology and protective behavioral strategies predicting alcohol use. And this is a Johnson-Neiman figure that shows the point at which messaging, positive messaging or negative messaging, begins to affect use of protective behavioral strategies on spring break. Obviously, this figure looks a lot cooler than this figure. In truth, they tell the exact same story, a very similar story. It really comes down to preference, which one you decide to use. All right, let's talk about centering. So what is centering? Centering is simple enough. It is when we subtract the grand mean, which is the mean of an entire data set for a given variable, from each individual observation. What that does is it tells you how far that person, that individual observation, is from the overall average of everybody. Why do we center? Well, It reduces the correlation between the multiplicative term, interaction, or polynomials and its component variables. You'll recall from ARM 2 when we didn't center and then we examined the kind of regression diagnostics, you see high levels of inflation and influence. But when we do center, those things are reduced and the correlation between the multiplicative term is reduced. It also makes interpretation of the parameter estimates easier. If you center, for example, in this equation, if b is centered or if x is centered or if x is not centered, b is exactly the same in this simple group. Down here, if you did not center, b is going to be different. M is going to be different. And this will remain the same. The effect of this slope will be the same. But centering will keep this slope consistent with this slope so that we're looking at the actual effect holding everything else constant at 0. That's why centering becomes important, because plotting interactions is much more difficult. When don't we center? If we don't center, when we don't center, there are people out there that will say that you should center absolutely everything. That will hold gender constant at its mean. I am not a fan of centering things like gender. Those of you who've taken class with me know that. I'm also, I would say that it is a bad idea to center when you have multiple conditions. Certainly, contrast coding works well when we have multiple conditions, and we talked about that in ARM 2. We're not going to do as much with contrast coding in this class, but if you have categorical variables, then I would advise against centering. Sometimes we don't like to center when we're talking about time, and sometimes we like to center at various values. Like if we want to start, let's say that we have an intervention and we have across 10 weeks. But the intervention doesn't start until week 2. You might say that for week 1, we're going to center on week 2, which means week 2 would be coded as 0, week 1 would be coded as -1, and so on and so forth, so that the intervention, the mean effect, is the intercept occurs at the intervention point. All right, so simple slopes. How do we calculate the value of y on x at levels of m? The most common method is to use plus or minus 1 standard deviation. So the way that we're going to do this, and you'll see this you did this in ARM 2, and we're going to do the same thing in ARM 3, is we'll form a new variable, and that new variable is going to be x times m. And then we form 2 new variables for m in order to test the significant indirect effects. We will subtract 1 standard deviation from m and rename this as high. I'll save this for class, but I always like to ask, why is it that we subtract 1 standard deviation to get a high value of m, and we add 1 standard deviation to get a low value of m? That's something that we'll talk about in class, and then we'll reform the multiplicative terms, and then you rerun the analysis at high levels and at low levels, and the effect of the slope of x at high levels of m tells you what the simple effect is when m is not held constant at its mean, but is held to a higher or lower value. You can also do a Johnson and Neiman technique for this and get the exact threshold where x becomes significant at high levels or changes at low levels of m, and then use that rather than plus or minus 1 standard deviation as your value. It's completely up to you. It works exactly the same way though. And so here's just an example of the equations where we have a test of simple slopes at low levels of m and at high levels of m. So this is an example of the write-up or write-up that I would use when writing up how to think about simple slopes. So we tested the interaction between protective behavioral strategies, PBS, and alcohol consumption. This interaction was statistically significant. Next, we examined this interaction by calculating the simple slopes of alcohol consumption on alcohol pathology at high and low levels of protective behavioral strategies. At high levels of PBS, the relationship between alcohol use and pathology was attenuated and not significant. In contrast, at low levels of PBS, this association was potentiated and statistically significant. So for your homework, for exams, this is the type of thing that I would expect you to do. And then when we're describing this, right, assuming that we're doing moderated mediation, we would then move on to the mediation effect. So what is mediation? In class, in ARM 2, I've often referred to mediation as the doorway between two rooms. And mediation is that door, and you open that door and you walk through. Do we need to center our variables for mediation? The answer to that is unless you are looking at moderated mediation, no, you don't need to center them. There's no need to center variables because when we're not talking about testing for some sort of conditional effect, all of the variables are going to be exactly the same. Mediation, in its most basic sense, conveys or implies some sort of sense of causality. But if we're not doing a true experiment, especially if we're using cross-sectional data and not longitudinal data, we need to be very cautious about how we refer to the language in mediation. I often do not say that X causes M, which causes Y, but I will say that there was an association between X, M, and Y. And to be honest, with mediation, you can kind of move those things around and you can test alternative potential models. If your data set is cross-sectional, you just need to have a very strong theoretical rationale for the flow of your model. So how do we specify mediation? We specify it in a kind of basic path model. So we've talked about this in the past. We have what is called like the A path, the B path, and the C path. And so in the past, we've done like just a simple regression analysis, right? The Barron and Kinney method, which we'll talk about here in a second, where you add this and this into the model, this and this into the model, then this and this into the model, and then all three into the model. And so first you're testing path A, then you're testing path B, then you're testing just path C, and then when you add all three of them into the model, you're testing what they call path C prime to see if there's a reduction in C. And if there's a reduction, then you say that you have what's called partial mediation. Of course, more recent studies have shown that in the past, Barron and Kinney said that this path, before mediation was included, the C path had to be statistically significant. More recent stuff by McKinnon has shown that C path doesn't ever really have to be statistically significant, and sometimes you have a fully mediated effect between X and Y, despite the fact that you don't have a direct relationship between X and Y. So early research used what is known as the Barron and Kinney method, which I just walked through. More recent research uses a path analysis instead of regression. You still see regression in the literature quite a bit. When we do path analysis, and we're going to do this in class this week, what we're really interested in is the overall model fit, and we're going to talk about what conveys good model fit and what model fit is, and we're also interested in the mediated effect. Now, previous research has looked at mediated effects by multiplying the simple effects, path B times path C, and then also looking at the total effects of path B times path C plus path A. So if we come up here, we have path A times path B. If we don't include this and we just look at this relationship, that's the simple mediated effect. If we include this relationship and then using the tracing rule add this relationship, then we will have what's called the total indirect effect. We'll talk a little bit about the tracing rule in class tomorrow, or this week. All right. Early research utilized tests of the mediated effect that were really just the standardized coefficient divided by the standard error of that standardized coefficient. So standardized coefficient would be this times this plus this, or just this times this. But taking the pooled standard error of those three coefficients, and multiplying out the coefficients, then dividing by the pooled standard error. And if that sounds like a z-test, you're right, it is a z-test, and that's what the Sobel test was a z-test. However, a z-test assumes a normal distribution, and what McKinnon has found is that across multiplicative terms, especially multiplicative indirect effects, we do not see a normal distribution, which means a z-test is inappropriate. Consequently, McKinnon has suggested using a bootstrapped approach, which we will do in class this week, to calculate the mediated indirect effect. So here is a mediated effect. We've got a model here. This is from a previous study that we did. And then you have a write-up that says there was a significant indirect association between negative emotion and alcohol problems via both coping motives and alcohol use. Combining these indirect associations with the direct association, that is right here, we have a direct association between alcohol use. And right here, the coping motive is a direct association. So you would say combining these indirect associations with the direct association, I'm sorry, this is the only direct association, resulted in a significant total indirect effect. So that's how I would describe that. All right, let's talk about moderated mediation or conditional indirect effects. Now, these can take a number of different forms, and people sometimes get twisted up in, is this moderated mediation or is this mediated moderation? You can save yourself a lot of confusion by just calling it conditional indirect effects. This means the indirect effects at varying levels of M. Of course, specifying the correct form of this is the most important aspect, and that means identifying the spot where moderation actually occurs. Once specified, the other piece of this is making sure that your error terms or your residuals are correlated appropriately as they would be in a straight regression analysis. One of the nice things about Mplus is that it does this for you so that you don't have to think about it. The way that we describe this is going to be much the same way that we describe moderation alone, but we're going to add a little bit of flair to it. So we have a moderated mediation model that looks something like this. We have the x variable affecting the y variable, and then we have M1. Some people will call this W1 because M can be confusing if you have a moderator and a mediator. I'm just calling it M1 here as the moderator and M2 as the mediator. And so in this case, you have M1 predicting M2 and M1 predicting the relationship between X and M. This, of course, is our volume knob. This is our indirect effect. We also have an indirect effect right here. We then, of course, have a different relationship where we believe that the moderation occurs right here. And so you would say that there's a relationship between this and X and Y, but that this link right here actually is affected by a third variable, or in this case, a fourth variable. Yeah, when we describe this, we would first describe the indirect effect, right? We'd say this indirect effect occurs. Then we would say, oh, by the way, there is a conditional effect on this path. And then we would describe the conditional indirect effects. When you describe this conditional effect, my preference is to have you include some sort of a test of moderation with the simple slopes. So your simple slopes would either talk about like how this slope right here varies at levels of M1, or if it's this way, how this slope right here varies at levels of M1. Then talking about the total indirect effect, which we will do in class tomorrow. That is it. That is just a brief kind of recap, or I mean, not necessarily a recap, but a brief kind of presentation of what you can expect this week in class. The data sets for class will be available prior to class, and we will work through this. That's it for today. Take it easy.